Our topic is electron beam lithography. Here are the members of our group. First, we would like to introduce photolithography. It is one of the most important steps in chip fabrication. It uses light to create or transfer pattern onto the wafer. The process is shown in this diagram. First, a layer of photoresist is placed on top of the wafer. Photoresist is a type of material that is sensitive to light, and it will change characteristics when exposed to light. This can be done by spin coating, as shown here. Resist in liquid form is dropped onto the wafer, and the wafer will start spinning to coat the resist. UV light will then start exposing the wafer through a mask. As you can see, some areas of the photoresist are exposed while others are not. For positive photoresist, the exposed area will become soluble, and for negative photoresist, it will be the opposite. So then we can put the wafer into a solution to remove the unwanted resist, and this process is called development. And note that photoresist is only a temporary layer we put on the wafer for patterning. We will then do etching or lift off to create the actual layer we want. Okay. Resolution of lithography is important, and the amount of diffraction will impact the resolution. We want to minimize the diffraction. And from this equation, we can see diffraction is related to the wavelength and numerical aperture. Changing the numerical aperture is not really practical because of physical limits and costs. This is the reason why the semiconductor industry keeps on lowering the wavelength instead. For electron beam lithography, EBL, the general procedure is the same as last slide, but electron beam is used instead of UV light. The wavelength of electron is at the level of a few picometers, which is why it has good resolution. It is also a form of direct writing, meaning it does not require a mask for the process. Since it does not require a mask before patterning, it is far more flexible when we want to change the design. And here's a comparison table for EBL and photolithography. EBL uses electron beams instead of light. It does not require a mask, and it uses electron resist instead of photoresist. And most importantly, it offers a really good resolution compared to photolithography of up to 10 nanometers. However, it is used typically for smaller areas. This is because EBL is a very slow process. Photolithography exposes a larger area of substrate at a time, while EBL uses a narrow beam to draw out the pattern. So it is a lot slower. This means EBL has very low throughput and makes it hard to be used in commercial semiconductor fabrication. However, it can still be used to make specific high-resolution design for some researching, or it can be used to make masks for photolithography. And this slide gives a general idea of the write time for EBL. And the time can be calculated from this equation. The dose here means the concentration of the resist layer. So from taking data from an article in 2013 to pattern an area of 1 cm square, it will take approximately 10 days to do so. In modern days, there are better methods to improve the write time for EBL, but it's still generally a lot slower than photolithography. And now for the components. The EBL machine has three major components. The first is the electron source, which will shoot out an electron beam to be focused by an electromagnetic lens system. The lens system can focus it to smaller than 5 nanometer in diameter. And then there will be a beam deflector which will deflect the electron beam to where we want it to be. The whole system uses CAD, which is computer aided design, and computer will control the deflector.
Now, let's look at the difference between etching and liftoff. The three graphs on the left indicate the process of etching, and those on the right is for liftoff. The purple thing represents the photoresist or the electron beam resist. We can see that some area of the resist has been removed during developing. We skip etching since we are only familiar with the process. And for liftoff, we add a metal layer on the whole wafer, then remove the remaining resist. We can say that etching is like subtraction and liftoff is like addition. Notice that in liftoff process, the area we emit electron beam is where we want it to rise, while etching does the opposite. And there is another animation for liftoff. In the case of EBL, we usually do liftoff instead of etching, since it performs better in the fine structures, and it is also suitable for smaller areas. Though EBL has excellent resolution, there are still some challenges. The first one is proximity effect. When the electron beam is emitted and bump into the resist, some of them penetrate the resist and even the substrate. We say that they are scattering, and we say the electrons that penetrate the resist in the undesired oblique directions to be forward scattering. And for those who reflect back to the resist, we call them backscattering. Though damaging the substrate is no big deal, however, the scattering electrons may contribute to unnecessary resist exposure, and they also excite the resist and the substrate, causing secondary electron scattering, which expands the undesired exposure. The phenomenon can be described by the sum of two Gaussian functions, where alpha and beta are determined by forward and backward scattering, respectively. Hence, we should take this into account and modify our pattern. For example, if we want the blue pattern to stay on or remove from the white wafer, we should deposit our electron beam like a red line. Higher positions means higher energy. Except for proximity effect, line edge roughness is also a challenge to EBL. Due to the imperfection of the whole process, the electron beam may deviate from our desired positions. This defect becomes more obvious as the size of the pattern becomes smaller, especially when we are drawing lines like the picture on the right. Unfortunately, this phenomenon is very hard to overcome, and it becomes the ultimate limiter to resolution in the case of optical lithography and a serious obstacle to EBL. Lastly, we talk about the applications of EBL. EBL has a variety of applications, such as electronic devices, optoelectronic devices, quantum structures, metamaterials, and it helps studies of semiconductors or superconductor interfaces, mechanical systems, optical and photonic devices, and more than that. Though we wanted to choose some of them and add it in our representation. However, our time is limited, so we will put them in the report. And this is the end of our representation. Thank you for listening.